In the deepest corner of the cosmos, an object lies that defies our perception of space and time. Meet ULAS J1342+0928, one of the most ancient quasars ever discovered. Its light has traveled to the Earth for around 13 billion years, dating back to the creation of the entire universe. At its heart lies a supermassive black hole that is almost 800 million times the mass of the Sun. An object this old and this mysterious shouldn't have formed so early in cosmic history. But here it stands, a beacon of light with a dark core, and an object that challenges our understanding of the creation of black holes and quasars. This is the story of ULAS J1342+0928. But how were scientists even able to find this object? Let's go backwards 8 years ago, and it's now 2017. In December of this year, scientists using the data in the Infrared Deep Sky Survey, which uses the United Kingdom Infrared Telescope, flagged a faint red region almost 13 billion light-years away. This survey was accomplished by examining the infrared waves that are emitted by all objects. These waves cannot be detected using traditional visible light telescopes, which could not detect the red-shifted ultraviolet light that quasars emit. This is why the United Kingdom Infrared Telescope was the only one able to detect it. Astronomers with this data looked at thousands of red dots, which represented several celestial objects, like stars or the quasars we are looking at today. Out of all of these dots, one appeared to stand out. Although it was farther away and fainter than the others, it caught the attention of an astronomer by the name of Eduardo Bañados, who decided to assemble a team of astronomers and physicists to investigate it further. Before moving on with the story, what does red-shifted UV light actually mean? Well, this is a concept in astronomy that explains how electromagnetic waves relate to the expansion of the universe. When the universe expands, the waves traveling from distant objects get stretched and become longer. On the electromagnetic spectrum, we can see that ultraviolet light has wavelengths shorter than infrared light. This means that when the UV light gets redshifted, the waves turn into infrared wavelengths. That's the reason we have to use an infrared telescope instead of a traditional visible light telescope or an ultraviolet telescope. Spotting this distant object was only the first step. Now the scientists wanted to understand and analyze what this object actually was. Bañados and his team first thought that the object was a brown dwarf, but as they collected more data, they found that this object was actually a quasar, something that they did not expect. After discovering that this object was a quasar, they had to collect data from multiple space telescopes to confirm their findings. The first of which was the Magellan telescopes in Chile. These telescopes helped the astronomers perform spectroscopy, which was a procedure that split the light coming from the object into a spectrum to examine the individual wavelengths. With the spectroscopy, the scientists were able to identify two features of the light. The first was the Lyman alpha line, which was a line of hydrogen atoms that acted as a cosmic fingerprint for celestial objects. With the discovery of the line, it helped the astronomer identify the redshift and the distance of the quasar from Earth. The second feature they found was the broad emission lines, which were used to calculate the quasar's mass. To calculate the mass of the quasar, the scientists first had to identify the width of the emission line. The thicker or broader the lines are, the faster the gas around the black hole was. Then they had to calculate the radius of the region of gas around the black hole. This is done by multiplying the constant of the speed of light, which is 3 × 10⁸ power, by the time delay of the light, which is how long it takes for light to go from the accretion disk to the gas clouds around the black hole. The scientists then used this equation known as the virial equation, to calculate the estimated mass of the black hole. The equation states that the mass is equal to the speed of the gas square multiplied by the radius of the gas clouds around the quasar. And all of this is divided by the gravitation constant, which is 6.674 times 10 to the negative 11th power. With the calculation of the mass, the scientists were able to get a detailed scope of what the quasar is. After using the data from the Magellan telescopes in Chile, the team had to check and finalize the calculations they did using data from the Large Binocular Telescope in Arizona and the Gemini North Telescope in Hawaii. The data from these telescopes helped them confirm the redshift, distance, emission lines, and the temperature of the surrounding gas. Having confirmed the details of the quasar, the scientists were able to turn their attention to what this finding reveals about the formation of black holes and our early universe. The one question that has been raised after the discovery of this quasar is, how is it so old? To understand the question and its answer, we have to dive into the early stages of the universe. Right after the Big Bang, free-floating particles roamed the universe. Stars and galaxies would not form until 200 million years later, with ULAS J1342+0928 existing 700 million years after the Big Bang. It may seem logical to think that the stars and dust clouds of the early universe collapsed into and formed this black hole. The main issue with this theory is that the quasar is too massive to form so early in cosmic history. For comparison, Sagittarius A star, the supermassive black hole at the center of our galaxy, is around 13.6 billion years old, but has a mass of only 4 million solar masses. In contrast, ULAS J1342+0928 already had a mass of 800 million solar masses when the universe was only about 700 million years old as we observe it through the light reaching us today. That challenges our understanding of how black holes form and grow. But scientists currently have a few theories on what might be the cause of the formation of this bizarre quasar. The first of which is that ULAS J1342+0928 formed from the direct collapse of massive gas clouds in the early universe. This is known as direct collapse. In this scenario, enormous clouds of hydrogen and helium collapsed under their own gravity. The collapsed clouds then create so much pressure that they condense into a singular point, known as a singularity, and form a black hole. Unlike the conventional creation of black holes by the collapse of stars, these black holes start with much more mass than the others, ranging from around tens of thousands to hundreds of thousands of solar masses. This head start might be what allowed ULAS J1342+0928 to grow to such a large size in a short period. The second theory is that ULAS might have formed from the rapid accretion of matter onto a black hole seed from a massive star. In this theory, a black hole formed from the collapse of a massive star or from a smaller scale version of the direct collapse theory. Mostly dust and gas are consumed, but other black holes and massive stars may be pulled toward the black hole. As the material spirals inward towards the black hole, the matter starts to form an accretion disk around the black hole, which emits a huge amount of energy and light, giving ULAS the bright disk that surrounds it and allowing it to consume more matter to fuel its growth. You can think of this like a whirlpool that keeps feeding water and other objects into the center. To further understand the mind-breaking details of ULAS J1342+0928, we have to understand a key concept in the limits of black holes. In black holes, there exists a theoretical maximum growth rate known as the Eddington limit. This states that if a black hole tries to accrete material faster than this limit, the radiation from the accretion disk will start to push away around gases, limiting further growth. This would mean that ULAS J1342+0928 is very close to said limit, as its luminosity is at the upper limits of what can be achieved. The third and final theory is that ULAS might be formed from smaller black holes merging and creating a larger black hole. In this situation, two or more smaller black holes would be attracted by each other's gravity. This would cause them to circle each other and start to merge, combining their masses, and give an explanation on how the black hole got so much mass in a short period of time. The theory is heavily debated, however, because there would have to be two black holes that are around 10,000 solar masses, which gives the same problem we faced early. However, this theory is still plausible. With the combination of these three theories, we might have a unifying explanation for the origins of this quasar. The scenario may play out like this. Just after the Big Bang, an enormous cloud of hydrogen and helium gas collapses into a black hole, causing large amounts of matter to be pulled in, creating an accretion disk that would further fuel the black hole's growth. At the same time, another nearby black hole would form in the same way. After both black hole seeds grew to large proportions, they would be attracted and merge, forming what we now know as ULAS J1342+0928. But this is only one possible scenario that combines the three theories that were explained. It does give us a scope of what actually happened 13 billion years ago. While the theories about the origins of this quasar remain debated, its true importance lies in what it reveals about the early universe. Unlike the black holes of our time, this quasar was blazing during the time that we call the cosmic dawn. Just like how dawn is what precedes the light of the sun on Earth, the cosmic dawn precedes the formation of the great stars that we look up to in the night sky. This quasar acts as a lighthouse in the darkness of the early universe, as stars just began to form and wouldn't light up the night sky like they do now. ULAS J1342+0928 stands as one of the most remarkable discoveries in modern astronomy, not only because of its size and bizarre nature, but also because of its help in understanding the early universe. Observing this quasar prompted us to create new theories and questions regarding the creation of black holes, stars, and galaxies. Overall, ULAS J1342+0928 is more than just a dot in the night sky. It is an ancient window into the origins of almost everything our universe has. If you reach this far into the video, I would like to thank you so much for everything. It has been my dream to create a YouTube channel related to what I love to learn about. From the rockets of our time to the black holes of the past, I hope to cover almost everything astronomy and aerospace have to offer. And that concludes the story of ULAS J1342+0928. So, thank you for watching.